and I'm going to welcome everybody to the 935th monthly meeting of the Amateur Telescope Makers of Boston, one of the largest astronomy clubs in the country, founded in 1934. We added to our ranks in the early 1970s with the inclusion of the Bond Astronomical Society. And I'd like to welcome everybody to tonight's meeting. I think you'll enjoy it. Our guest speaker tonight is Dr. Anna Bonaca. She's going to talk about star streams in the Milky Way Galaxy. So without further ado, I'm going to try so you don't see too many of these arrows and things. The agenda is the agenda. You guys know it. You folks know it really well.
How's that?
It's good. There you are.
Do you have that slide of the t-shirts?
I do, of course.
I think that was the first slide. Yeah. Yeah, it's just going to be the holiday season. And I went online. I thought these would be very appropriate t-shirts, but it's there's a lot of good ones out there. And I found a couple I especially liked. The first one, all I care about is astronomy and like maybe 3 people. So if you wear that t-shirt in the clubhouse, be ready to tell somebody if they're one of those 3 people. And very appropriate for these particular COVID times. Warning, I test possible for stargazing. So there's a lot of other ones out there as well. I know Caitlin Galetta's in the audience there, and I saw her at Stellafane a couple of years ago, and you could buy a t-shirt that has your name and then observatory below it. And that one was the Galetta Observatory. I had the Chapel Observatory. So there's a lot of t-shirts out there. A good idea for a holiday present for somebody. Now we'll go to the next slide.
Do you want to go to the first slide again, or you want to go to your,
yes,
you want your
sure.
quote?
And our saying for this particular month came from none other than Stephen Hawking: to confine our attention to terrestrial matters would be to limit the human spirit. Again, very appropriate for the COVID times. I think there's nothing better, and you're hearing all this news about how bad things are getting, just to go out in a clear night and look at the stars and just get away from it all. So that's just my thought there. That's a good reason for being an observer.
Great.
Now we'll go on with the next slides. So a couple things going on between now and our next meeting in December 10th. The Leonid meteors will be coming up. Again, that's not the shower it was back in 2001 or whatever it was back then. You see about 10 an hour. And just an experience I had one time, for whatever reason, I went out for an early morning walk. I couldn't sleep. And I just happened to catch a meteor out of the corner of my eye. I looked up and went on with my walk, but I kind of kept looking in that area of the sky just in case. And sure enough, I saw another one. And I think in the course of a 15-minute walk, I probably saw 3 different meteors, and I noticed they were radiating out of the constellation Leo. And back then, I didn't know the dates of particular showers. So I went inside and looked, and sure enough, I was out in the morning of the 17th of November, and what I was seeing was a couple of Leonids. So they're out there. The peak comes out in the early morning hours, sometimes after midnight when Leo gets a little higher up in the sky. So again, it's a minor shower, but if you can't sleep, whatever reason, instead of counting sheep, you can count Leonids, and hopefully you'll see a few of them. Jupiter, Saturn, and the Moon are grouped together on Wednesday and Thursday evenings, November 18th and 19th. And as we were talking about, those 2 planets will be in a super conjunction on the 21st of December. They'll be a few arc minutes apart. So you'll catch them easily in the same field of view, telescopic field of view, a high power field of view. I read somewhere there'll be a couple of Jupiter diameters apart. So this is it's a once in a lifetime event, because these are the closest in literally centuries. The problem again is they're going to be very low in the southwest sky after sunset around that time. So you want to plan ahead and find an area that's got a wide open horizon. I don't even know if the view from our clubhouse, it's pretty open there. I don't know if that would be open enough. I think the trees would be in the way there. So you got to really find a good open area, but it's worth a look-see. They'll also be within a degree or so of them each other for a few days before and after that. So if we don't quite catch it on that evening, which will be sad, we'll still be able to see them together in the same low power field of view. On Monday, November 30th, the penumbral lunar eclipse will be at its greatest depth or eclipse. And again, these are kind of minor. They just the moon look a little bit gray or kind of shadowed in one particular area. But if you can't sleep on the morning of November 30th, take a look-see and see what you can pick out. And then finally, and I was harping, I don't want to say harping, but I was encouraging people to do a little variable star observing by checking out SS Cygni, and that's coming up in this report. But on the 8th, Algol, the eclipsing binary star Algol, will be at minimum. And this star, I put down 8:38 p.m. I had a couple of different readings. I think Sky and Tel might have had it at 8 o'clock. The AAVSO had it at about 8 o'clock. The Sky and Telrad, I think, had it at 7:30. The AAVSO had it at 8, and the observers guidebook from the RASC had it at 8:38. So somewhere around 8 o'clock, give or take a half hour, it'll be around minimum. And it goes from about 2.2 magnitude down to 3.5. It's a noticeable change. I will try to set something up for that. I'll try to send something out so we can have a club observing, if you will, of that. We did that at the Clubhouse a number of years ago, and I was hoping to do it this year. That's obviously out of the question now, but I'll try to set something up on that particular evening as we see what the weather's going to be like. But that's a neat star to look at. You check it out probably once every 15 minutes is a good time element on that. And the moon will be in the morning sky, so it won't interfere at all. Next. The sky object for the month, Observer's Challenge, is the galaxy NGC 278. And if you look at the chart on the left, there's a constellation Cassiopeia. And usually when we think of Cassiopeia, we think of open star clusters. The Milky Way runs right through that constellation. And all those little yellow circles you see in that chart, those are all clusters. We have some good ones like NGC 457, the ET cluster, and 103 is there. And a couple of other ones, 225, 129 are neat ones too. But if you go to the very lower, the southern part of that constellation, you'll come across a couple of galaxies. NGC 147 and 185 are satellites of the Andromeda Galaxy. They're rather large and faint. NGC 278, that's our challenge object for the month. And I found that one by looking for the star Omicron and Pi. You see a row of stars there. I don't know if Rich can point it out with a pointer on the computer there, right there. And if you look at the chart on the right, this is made from the AAVSO website. And I'm just going to move some stuff out of the way here. And at the very top is Omicron Cas, at the bottom Pi Cas. Rich has labeled them. Thank you for doing that, Rich. And if you look from Omicron Cas itself, and just a little bit below, there's a 5.7 magnitude star. And you look across toward the middle, there's a 7th magnitude star, roughly in the middle of that field. The three form a kind of a right triangle. And that's about a degree from that 5.7 magnitude star to the 7th magnitude star. And another about a half a degree beyond, and there you see NGC 278. And I don't know if Rich can point these out, but if you look at NGC 278, you just put the cursor right on that. Now look just a little above, there's a star right above it. And that's about a 9th magnitude star. And from that star, just a little bit up to about, say, 1030, it's a little star just above that's the one. Now, if you go in the other direction, down a little bit, there's another star. Now, I do want you to look at those three stars and the galaxy. And we're going to go to an image that Mario Mata took. Take a look at the next slide. And there are those stars again in that field. The one just above, there's NGC 278 in the middle. And just above it is that brighter star I was talking about. And there's that little one. So that's the field of view. And we also, next to that, by the way, this galaxy, a little background, it's a spiral type galaxy, pretty much face on to us. It's about 40 million light years away. So you're looking at light that left back when the horse was about the size of a fox terrier. And it's an interesting galaxy because it's in two parts. And Doug Paul's picture just to the side there shows a little bit more of a close-up view. But it's an unusual galaxy because it's got two parts almost. There's a heavy amount of star formation right in the central part of the galaxy. And then there's an outer shell where not very much is going on. So it's interesting to that aspect. Now we'll go to the next slide, which is a sketch I made. I believe we've got that. Oh, we don't have the sketch. Okay. Well, you know what? My sketch was exactly like Mario's. Every star there with my little 10-inch scope. I was seeing down about 20. So just look at Mario's sketch, and that's what I drew. It's almost the same exact thing, right down to 20 magnitude stars. What I will say, though, is I was able to see that galaxy with a 4.5-inch scope as well. The sketch I made was with a 10-inch, but it was visible with a small scope, which surprised me because it's listed as 11.5 magnitude, and that should be really the struggle for 4-inch scope. But from what I read about this galaxy, it has a very high surface brightness, especially the nucleus itself. And to me, the galaxy looked very much like a planetary nebula. It had that same type of appearance, especially in that little 4-inch scope. And then, Rich, I guess you're going to pick with something about Comet Atlas. Think you got to unmute yourself, Rich.
I tried using the space bar, but it didn't work. So there's a comet in the sky right now. It's passing by the constellation of Orion. This was a graphic from Bob King's article in skyandtelescope.com. It's passing close to the Earth this weekend, and will be very close to Bellatrix right here. It's not particularly bright. I tried to see it in a pair of binoculars the other night, and I could not. But my skies aren't very good. It's very green, round. It's no comet NEO-wise, but it's just, there it is. It's a relatively pretty comet to look at. So I just wanted to include that as part of the observer's report. Glenn, there's your SS Cygni graph.
Okay. Yeah, this is a light curve of SS Cygni for the past couple of months. It's I think about 2 months. And I've just got to move some stuff that's on my screen. Rich has it in Julian days, and usually you can also get a plot for the dates. So I'm not sure, but I took some notes on this. The outburst you see over at the left-hand side there, that was back around September sometime. And the most recent one came up right around the latter part of the month, later part of October or so. It went up to probably about ninth magnitude. It wasn't a particularly bright outburst, but it was there. And I guess before I go any further, and I had to take a lot of notes on this, so I gave everybody credit. I just want to say a note of thanks to those of you who took the time to check this out. And in particular, Mario Mata, Doug Paul, and Joe Rothschild actually took some images, and I'll show those a little bit later on. They imaged this both before the outburst and during the outburst. And Rich himself, our president, made some estimates, and of course I do that anyway for the AAVSO. So we had this star pretty well covered. And as I said, sometime around late October was when this star started to get active. The recent outburst began around October 28th. And it reached about just about 9th magnitude. Some people had it as bright as 8. You can see it on the chart there that Rich has. Some had about 8.7 magnitude. Most people had it around 9.1, and that agreed with the estimates that our club members made. Most had it at about 9.1 to 9.3 at outburst. It stayed up that way for about 6 or 7 nights, and then it went to below 9.5, and it's right now again around 11th magnitude, bouncing around. And I just wanted to throw this out to those of you who didn't see it. I really encourage you to give this a try. It's a fun star to look at. If it behaves the way it normally should, which is about 50 days between outbursts, the next outburst should occur sometime in December, and signals will still be high enough in the sky to follow this star. I would encourage you, if you didn't look at it this last time, check it out. And if any of you didn't, I sent out a chart to the membership prior to this whole session that we had. But if anybody either just misplaced that chart or they didn't get one, email me and I'll send you out the charts and the details you need to follow SS Cygni again. The first night is probably the biggest one. It's just to find that star the first time. But you go out on subsequent evenings and you want to look at this every clear night. It gets easier and easier to you literally just find it within a minute or so and make an estimate. So great star to look at. And for those of you, by the way, that aren't familiar with this type of star, what it is, it's a binary system, very close. The primary star is a star very much like the sun, and the companion is a white dwarf. And anyway, we'll go on. What happens is the white dwarf accretes material from that star, eventually becomes unstable and has an outburst. Now, these two pictures are from Mario, and the arrow shows SS Cygni. And if you look over the one on the left, there's that triangle, and I'll talk about that a little later, but it was inside a triangle of stars, and the star immediately to the left in that first picture, that's the 8.6 magnitude star. It's also accompanied by Mario's, it's actually a quintet of galaxies there that it appeared in Mario's picture here, but that's SS Cygni during its quiescent phase. It was probably about 11th magnitude when that picture was taken. Now look across to the right, and there it is during outburst, and at that time it was probably a little bit above 10th magnitude, maybe a little in the low 9s. And if you just look back and forth, took your gaze back and forth at SS Cygni, and you get this kind of a blinking on and off type of thing. It's an amazing star to look at. And it is one of the most popular stars in the AAVSO's repertoire. It's been observed almost nonstop since I think it was discovered around 1901. We'll go to the next slide. If we have a next slide. Oh, we don't have any other slides? Okay. I had a couple of the slides. They're not there, but what I'm going to do while I still have I'm still on here, I'll send some pictures to Al Takeda to put in the newsletter, because we also had some nice pictures from Joe Rothschild, and Doug Paul had a nice set of pictures of the two side by side again during the when it was during its quiet phase and then during the outburst. And I think that's about it then. If anybody has any questions or comments, feel free. And until then, keep looking up.
It gives me great pleasure to introduce to you Dr. Anna Bonaca, who will talk about star streams in the Milky Way Galaxy. She's a fellow at the Institute for Theory and Computation. She is hosted, I'm going to get this out of my way, hosted by the Center for Astrophysics through Harvard Smithsonian. Her specialty is stellar dynamics. I can't wait to hear how these star streams form, and I want to hear more about the dark matter halo that surrounds the galaxy. So I'm going to unshare my screen. If you want to all unmute yourselves, we could give her a very large ATMoB round of applause. Yay.
Yay.
And Anna, I'm going to let you share your screen.
Sounds good. Okay, you should be seeing
Yeah,
my title slide now. Great.
there you go.
Well, thank you for having me. And yes, as Rich said, I'm an astronomer who studies dynamics of stars. And one thing we learned, well, we as astronomers learned all the way back in the 70s is that stars in galaxies move very fast. So fast that if really all there was to galaxies is what we see, they would just fly away. Instead, because we do see galaxies remaining such beautiful, nice objects that we can take pictures of and just like enjoy with our naked eyes as well, we think that there is something more to it than meets the eye, that all of the galaxies are actually surrounded by massive halos of dark matter. And the big question is, what is this dark matter and how much there is of it in the Milky Way, and how it's distributed. And those are all open questions, and I'll be talking about how I'm trying to address them with like this very interesting objects, the so-called stellar streams. And I will get to what they are along the way. And so these objects, let's start with, are orbiting the Milky Way Galaxy. And one kind of embarrassing thing for an astronomer studying the Milky Way is that, like, until very recently, we didn't even really know what the total mass of the Milky Way is. And so it was a big kind of news splash that happened a year and a half ago when astronomers combined the information from the Hubble Space Telescope and some of the new measurements from the European Gaia satellite to measure exactly how massive the galaxy, like the Milky Way Galaxy, is. And it ended up that the total answer is 1.5 trillion times the mass of the sun. And it was a big deal because if we sort of count up everything that we see in the stars, and gas and planets, which are really just very small parts. So everything that we see anyway, we only get to something like 70 billion masses of the stars, of the sun. So this means that almost 90% of the mass in the Milky Way is in this form of dark matter, and it's virtually invisible to us. So it is like a huge component of not just our galaxy, but also the universe overall, as it turns out. And of course, we'd like to understand it. That's I guess, in our nature as scientists to ask questions, and this is like a really big one. It's 90% of our galaxy. And people have been looking for it. there kind of been proposed different ways to detect dark matter. So I think that we saw it like interact gravitationally, so it's keeping the galaxies together. But we're thinking, okay, maybe if it just like doesn't interact with ordinary matter very often, but maybe sometimes it does. So there are now multiple experiments all across the world, and one of them is this LUX experiment in the old mines in South Dakota, where they put these giant tanks of xenon, like the noble gas, that hardly interacts with anything else. So they buried it under the ground and are basically just staring at it, hoping to see some signature of dark matter passing through this tank and interacting with the xenon. And really all that has happened is that we were kind of just been able to rule out some certain models of dark matter because we haven't detected anything yet. But then there are different ways. And then people are saying, okay, maybe if dark matter doesn't interact with ordinary matter, maybe it can interact with itself. Maybe it annihilates. And so, and if in most popular models of dark matter, the annihilation would produce gamma rays. And so one of the Fermi satellite has, among other things, been launched to see if there are any gamma rays produced in centers of galaxies that could presumably come from dark matter. And so there have been some exciting news, but then it ended up being always something else, mostly the pulsars that caused those gamma rays. And those are already pretty big investments. So LUX was something like $10 million, like the Fermi satellite is $600 million. And then finally, the CERN spent $8 billion to construct the Large Hadron Collider. And now people are running experiments trying to produce dark matter in lab, but still coming up short. And so despite all of these different ways of kind of how we think we might detect dark matter, really the only one that we know works is that we can see how it pulls on the stars that we see in the galaxy and try to infer anything we can about it from this gravitational interaction. And what's really important and kind of on this gravitational effects of dark matter is a little bit of how it's distributed. So we know that dark matter halos surround galaxies like the Milky Way. And so here I'm showing a simulation of the most popular model of dark matter. So this is a simulation of a Milky Way-sized galaxy. However, the actual disk of the Milky Way would be just like in this very, very central part. And all of this rest is this giant dark matter halo. And as you can see in this model, where the particle mass is something like a mass of the proton, there are a lot of these clumps of dark matter. As you can imagine that as those clumps move around the galaxy, they might be sort of causing a little bit of perturbation to how stars usually move. And this is a specific feature of this particular model when these dark matter particles are very heavy. If they're slightly a lower mass, and in this simulation, if we started exactly the same way, obeying the same laws of physics, just assuming that the particle mass of dark matter is slightly lower, so something like less than an electron mass, we would get a dark matter halo that on large scales look pretty similar to one on the left hand side picture, but you can see that it has many fewer of these smaller subhalos that are orbiting. So in this situation, and we call this model warm dark matter because the particles are lighter and therefore kind of can attain higher velocities. We expect there to not be that many perturbations to how stars move on these small scales. And finally, one model that has kind of recently been proposed is the fuzzy dark matter model, where the particles are extremely low mass, so something like 30 orders of magnitude lower than this preferred cold dark matter model. And they're so low, such as the the quantum effects become observable on astrophysical scales. And so what you're seeing here is this kind of fairly uniform field, but with a lot of quantum fluctuations that change in time. So there are no sort of massive clumps like in the case of the cold and warm dark matter, but there's still a lot of perturbation from this constantly changing field. And so my personal research goal is to map the dark matter in the Milky Way on these very small scales and try to distinguish which one of these models is actually correct, or at least closest to what we see in the Milky Way. And as you can imagine, it's not easy mapping out something that is invisible and doing it with high precision if we're really interested in this like very smallest clump that would have like the least amount of gravitational pull on the stars that we see moving in the Milky Way. However, it turns out that a phenomenon that we are probably all familiar with from our everyday lives can help us in that regard. And to sort of roll it in, I will start with a question for you. Does anyone care to guess what this picture is showing?
Tide?
Yes, it's a low tide in the Boston Harbor. And the way it comes in is that tides are also created through gravity. And so in the very sort of cartoon picture, what happens with tides on the Earth is that we have the Earth and the Moon system. And the Moon, well, they both gravitationally pull each other, but now we'll sort of just look at what happens on the Earth. And if we kind of look at this line that connects Moon to the Earth, we can see that the gravitational pull of the Moon is felt most strongly on the side of the Earth that's closest to the Moon, and then less strongly at the center of the Earth, and then least strongly on the opposite side. So if we sort of subtract this middle arrow and sort of just look at it from the perspective of the Earth, what forces are felt, it would be sort of that are like these tidal forces that are pushing towards the outside from the Earth center. And again, in this like very simplified picture that because Earth has like this giant body of water that can be stretched out in this more oblate shape, which then causes tides twice a day that we have. And really what is important here is sort of the ratio of the gravitational pull from the Moon versus the sort of gravitational pull from the Earth itself on us and including the oceans. And so what I did as a sort of a simple exercise is derive an expression between the tidal accelerations. So this is just a gravitational pull, the tidal pull of the Moon with respect to, and sort of scale it with the gravitational pull of Earth itself. And it turns out that it really only depends on 4 quantities. And one is really actually only 2 quantities because it's just a question of ratios. So the important numbers are the ratios between the Earth size and the distance between the Moon and the Earth. So this is the lowercase d and the uppercase r. And then the mass of the Earth as uppercase m and the mass of the Moon, which is a lowercase m. And it turns out, anyway, this is the expression. We are not going to derive it here. But I have another question for you now. Is like, does anyone sort of know at least kind of approximately what are these ratio? What is sort of the distance between the Moon and the Earth in terms of Earth radii? And what is the sort of how much more massive is the Earth compared to the Moon? Guessing is totally fine.
The Moon is 30 Earth diameters away.
I think that's pretty close. Yeah. Do you have any takers for the mass ratios?
No, I don't actually.
It's also, anyway, like what do we, astronomers also very much like to do is say order of magnitude, and this was exactly the right order of magnitude. So it was like the, between 10 and 100, it's like the correct answer. So it turns out anyway that the exact number is at 60. Oh yeah, I guess you said the total diameter, right? And so I just like had it as a radius. So that's turns out being 60, and that the Earth is 81 times more massive than the Moon. And so when you crunch the numbers and then put these ratios in the equation, it turns out that the gravitational pull of the Earth itself is much stronger, so that the tidal force of the Moon is just like 0.00001% of the gravitational force of the Earth. And that's the reason why, like, we are not losing our oceans; they're not being pulled apart by the Moon tides. It just like gets slightly elongated, and kind of Earth gets into this kind of squash shaped. But why the reason I started with this is that this exact picture really holds for some other objects that we have orbiting in the Milky Way Galaxy. And as it was sort of a premonition from Glenn when he talked about the open clusters in Cassiopeia, because the star clusters are actually the objects that we'll be most interested in. So if we just look at a star cluster, and again, this is, pretty much like the one before, not drawn to scale at all. But if we consider a star cluster, which is orbiting kind of around in the Milky Way disk, around the center of the galaxy, we can kind of set up the exactly same situation. So we have a star cluster of some mass and some size. It's at a distance from the galactic center. And sort of the enclosed mass within this sphere is what's basically causing this tidal pull. And for a typical star cluster close to the sun, sort of these are the ratios. So the galactic center is much further away than the Moon is from the Earth, but then also the galaxy is like much more massive than the star cluster. So these ratios are a little bit different than what we have in the Earth Moon system, but the physics is the same. And so, time for more questions for you. Let's look at a couple of famous star clusters. I'm sure that everyone knows which are what's shown here, but yeah, let's hear it.
Pleiades and Hyades.
Yes, we have Pleiades over here and Hyades down there. And so if we kind of calculate what is this ratio of tidal forces with respect to their own gravity, they're like in the percent level. So for Pleiades, it's 5%. Tidal forces are kind of 5% of the gravitational pull, and for Hyades, they're 1%. That means that like these tidal forces here are very important, and actually they start slowly can start pulling stars out of these clusters. And what we think happens is something like this. So now I show a simulation of a globular cluster orbiting the Milky Way Galaxy. And now we are sort of seeing the galaxy edge on. So this razor thin line is the disk, and the star is the position of the sun. So as I play it forward, you can see that the stars are starting to escape from the main cluster, and they're kind of being pulled out of into the body of the Milky Way, and they're on slightly different orbits. So the stars that are kind of leaving towards this inner part, towards the galactic center, they're moving slightly faster on slightly shorter orbits, and the ones that are kind of escaping through on the other side are moving slightly slower and kind of lagging behind. And what then ends up happening is that these stars are forming this a structure that we call a stellar stream or a tidal stream, because it's caused by tides. And the exciting part is that we actually have observed these objects. So here is a map of stars observed by the Dark Energy Camera Legacy Survey, centered on the globular cluster Palomar 5, so right over here. And you can see that it shows these beautiful, massive tidal tails that look a little bit different from the simple explanation that the simple picture that I show in the movie, but actually are there. We have the cluster and these two tidal tails. And because, as you saw, this globular cluster is sort of orbiting a big part of the galaxy, we think that, and it's caused by the gravitational forces or the tidal forces of the Milky Way, we think that it's sort of a record keeper of what it has encountered on its way around the galaxy. And in what I showed in the simple simulation was something that looks like this, where you have just a very idealized situation. The galaxy is completely smooth. There's like really nothing happening. There's just like one smooth dark matter halo. And in the smooth galaxy, we expect the stream mostly to be smooth like this. Maybe there are like slight kinks or like slight overdensities, but by and large, like in this model, the stellar streams in the Milky Way would look like very simple kind of one-dimensional objects. And this is something like what we would expect if the dark matter was a light particle, when there are no small clumps that are kind of messing up or orbiting the galaxy. However, if they are present, then they would interact with stars in the stream. And at some point, some clump might pass by and sort of scatter stars out of the stream, causing this sort of patterns of overdensity and underdensity. And maybe if like there are particularly massive clumps passes next to the stream, it might even detach part, kind of one chunk of the stream. And so this is why I'm mostly excited to study stellar streams, because in a way they are sort of a litmus test of what is out there in the galaxy. And so really what we want to know is whether the observed streams look more like the one on top, like these smooth, regular looking objects, or whether they show these interesting features of that are some evidence of perturbation. And to do that, we need huge maps. You saw that like those are large objects, and like we need big maps, like basically all sky maps of distant stars in the Milky Way. And here's one such that I made a number of years back, coming from the Sloan Digital Sky Survey. And so here, this is showing the view of the stellar halo of the Milky Way, where I selected stars that I expect to be fairly distant, so between at 8, 15, and 20 kiloparsecs. And sort of that's kind of how color coding here works. And so you can see that at first, like the thing, yeah, it's like very, very homogeneous. There's a lot of structure here. And these small groups of stars, like small overdensity you see, those are the globular clusters and dwarf galaxies that are orbiting the Milky Way. But the sort of most prominent features are these wide swaths, and those are the stellar streams. And the most massive one over here is the Sagittarius stream, which is the tidal tail of the Sagittarius dwarf galaxy. The kind of next in size is this so-called orphan stream, and it's called orphan because we don't know what was the progenitor object of this stream, but we think it was a low-mass dwarf galaxy because it's still fairly wide. The Palomar 5 globular cluster I showed you before is here in the corner, just like not observed in as much detail or as further down, it kind of cuts short over here. And the object that I'll be talking for the most part from now on is here, starting at this bottom right, and then in an arc going all the way up to the top left. And this one is called GD1 for its discoverers, Grillmeyer and Dionatos. And we also don't see a progenitor object here. We think it was a globular cluster just because it's sort of similar in width to this Palomar 5 tidal tails that we know are originate from a globular cluster. And this is because this object is so long um, and kind of so far out of the Milky Way disk, we thought this was a really good object to use as a test of dark matter. However, you can see that like in this map, it's kind of hard to tell whether there is any structure. Like to first order, it looks kind of smooth, but then if you look more closely, you might say like, oh, maybe like there are some gaps over here, but then you check how much variation there is in the Milky Way kind of smooth areas kind of outside of the stream, and you see kind of there are like similar variations. So for a while it was very hard to make this measurement because we just couldn't select members of the stream star of the stream very well. However, that all changed with the Gaia mission. And so here is the image of the full sky created by this Gaia satellite that, in addition to measuring very precisely the positions and colors of stars, or rather, because it measures positions of stars so precisely, and it keeps doing that all the time, it just continually scans the sky, and so that so precisely that it can actually detect the motions of stars. And so now, instead of just like having this static view of the Milky Way, we can animate this kind of into the future and see that some of these groups of stars are the open clusters are all moving in the same way, and also whereas the stars that are not a part of the system are kind of moving more randomly in this field. And this was very, very exciting in the field of Milky Way science, especially dynamics, which is the part that I am doing, because it now really allowed us to kind of not to kind of play out the movie and select stars in a different way. So a collaborator of mine, Adrian Price-Whelan, and I, basically on the day of this data release, looked up this GD1 stellar stream, the long one that I showed before. And so we selected stars from this Gaia catalog in the right part of the sky and focusing just on the distant stars. So we expect are further away than 1 kiloparsec. And here I'm just showing the distribution of these stars. And there's really nothing there, or rather there's like this overdensity, but this is just because this gets into the region of the Milky Way disk. The sort of coordinate system here is aligned such that the stream would appear as an overdensity at this phi2 coordinate of 0. And just with this one selection, you don't see much. However, if you take all of these stars and look at the proper motion diagram. So here I'm showing the sort of proper motion, so velocity on the sky in the x direction and velocity on the sky in on the y direction. You can see 3 distinct clumps. So there's one over here, which ends up being the motions of the typical halo stars in this part of the sky. The huge blob is the motion of the disk stars. And there's a small blip, which ends up being stars of the stellar stream that we're interested in. So if we just select stars in this yellow box and plot them on the left, we already see a stream shaping up over here, which is pretty exciting because it was literally just kind of 2 conditions that we put on this catalog. Then we wanted to refine it a little bit more because we still have all of the color information that we used previously to select stars that kind of have the same age and similar distance. So if we plotted the color magnitude diagram, so with the color on the x-axis and bluer being on the left-hand side, you can see that there's this overdensity, like the main sequence of stars on the blue end of this distribution. So if we only select those stars as a kind of clear separate population, we are left with a figure on the bottom left. And so now here I'm showing what we think are the likely members of this GD1 stellar stream. And you can see that there are barely any stars left in star kind of locations of this diagram that are at large or very small values of the phi2. Most of the stars are in this one single track. And that was very exciting because this was for the first time we could actually see a stream in a lot of detail. And the first thing that we noticed is that, oh, it extends actually almost 20 degrees longer than what we previously knew, because now we're just like able to see this very low density part of the stream. We could definitely say, oh, these are actual gaps in the density of stars along the stream. And this one in particular looks interesting because it looks like it has no stars in the stream, whereas here there's still a little bit of them left compared to the field locations outside of the mainstream. But what surprised us the most was that there looked like there's like a little bit of an overdensity of the stream-like stars that are outside of the mainstream, like in this spur over here, because it just like looks more like a spear, and this blobby, more diffuse feature here on the bottom. And I was very interested to see if I could actually create such features by bombarding the stellar stream or model of stellar stream with something like those small clumps of dark matter. And it turns out that the answer is yes. So here is a model of this GD1 stellar stream that 500 million years in the past encounters a massive object that sort of gives a velocity kick to the stars that it came closest to in the stream. And they are moving this sort of ring that is orbiting around the main part of the stream. And so when we sort of project it at the present, you see that this location where the impact happened has a small underdensity of stars, and those, because they have been kicked on this orbit that in projection look are like they're offset from the mainstream. And so if we sort of project it on the sky as observed from the Earth, the model is on the bottom and our observed stellar stream is on the top. And you see that they look very similar, that it has this gap at this exact location that we see it. And it's kind of a fairly big gap of something like 10 degrees. And it has this spur of stars, the same as we observe in the data that kind of is separated by a degree. And it's also something like 8 degrees long. And we're like very excited because to make this model, here are some of the parameters that we used. And in particular, this one was interesting. The total mass was 5 million solar masses. And this was kind of in this very interesting regime, because if this was dark matter, it might be one of those dark matter clumps that we were set out to look for initially. However, it's this is not just from this evidence we can say. We only know that something of this mass could have produced this result. So now there is kind of another part where I asked for audience participation and ask who might have perturbed the GD1 stream. It's a whodunit.
Black hole?
Black hole, yes, definitely. Next.
Globular cluster.
Globular cluster, excellent. Any other ideas?
I thought maybe a satellite galaxy of some sort.
Ooh, really good. Milky Way satellite galaxy. Yes, those are all great suggestions, and really, and I will just add like, or better, the one I mentioned at the beginning was the clump of dark matter. And so these are all in this same like massive regime of like kind of compact objects that are orbiting the Milky Way. But they're also all very different in nature. So how would you say, how can we distinguish them? what could we measure to tell them apart?
Mass?
Mass, yes. What else?
How about the physical dimension?
Oh, the size, yes. They are very different, can be very different sizes. Anything else?
Maybe the duration of the impulse, how fast it's
Ooh.
moving past the star stream.
Yes, excellent. So this is a very good, like the saying that the impulse actually combines two things. It's kind of how fast is the duration and sort of how close it came to the stellar stream. So I just was being cheap here, or like cheated a little bit, and just chose these three: the mass, the size, and the closest distance, or like the closest approach. And yeah, so let's go next, see kind of whether we can rule out some of these objects based on of the observations of this feature we have. And sort of to kind of guide us through this, I created a series of kind of controlled numerical experiments where we have like this in the middle panel will be our fiducial model of the stellar stream that has kind of the gap that kind of fits and the spur size that fits, and in each column I'll vary only one parameter. So in the first column I'll just vary the mass, so fixing all of the other parameters of the impact the same, just changing the mass. So you see if the mass was lower than what I showed previously, both the size of the gap and the size of this loop is smaller. And if we increase the mass, both the size of the gap and the size of this spur grow. And this is very similar to what happens when we change the size. So as we might expect, if we have a more compact object, so with a smaller size, it would have a larger effect with the same mass. So again, if it's an object, something like black hole, which would have a size of 0, basically, then we see that it would create a huge, huge loop or huge spur. And if it was something big, something like 100 parsecs wide, which is coincidentally what we expect for dark matter subhalos to look like, it would barely have any effect on the stellar stream just because the density of this object is so low. And finally, I'm showing here how the properties of this impact depend on the distance or the closest approach. You can see that as expected, much more of an effect is if the object comes very close to the stellar stream. So our fiducial model is that it comes at 15 parsecs. At a distance of 50 parsecs, there's really barely any effect. There's a little bit of a gap, but not much of a spur. And if it comes very close, there is the same gap that we expect and a huge spur happening. And so it turns out that because it looks like that this object should have come very, very close to the stream, that we can actually rule out many of the objects that were suggested previously. So I'm here showing what is the relative distance between that part of the stream and the known globular clusters and the dwarf galaxy satellites of the Milky Way. And I guess the classical are the more massive one, and the ultra faint ones are the more recently discovered lower mass ones. And you can see that they never really come very close. So this is, I guess, I'm showing on the y-axis the relative distance in parsecs. And it's, kind of hovers around 10,000 parsecs or I guess 10 kiloparsecs. Whereas as I showed, what we kind of the need is something on the order of tens of parsecs. And even if we kind of are being generous and asking, has anything come within 60 parsecs of the stream? It really hasn't. None of these objects, at least not in the past billion years or so. And so I think we can at least this favor saying that these are some luminous objects, or at least ones that we know of and have their orbits at the moment. We can put some constraints sort of considering simultaneously like the mass and the size. And as we saw, we really are preferring those more compact objects. So this would be the ones that have sizes less than 30 parsecs, and they are fairly massive. And as I showed previously, or kind of hinted at, it turns out that dark matter subhalos are not quite as dense as we expect. So it turns out that there's this very kind of small overlap where we expect dark matter subhalos to be, and the kind of properties of the mass on the y-axis and the size on the x-axis that we expect for the object that hit the stellar stream. On the other hand, yeah, like that black hole, so that means that that black hole solution is still very much alive. It's just that astrophysically, we don't really know why would a massive black hole be doing roaming around in the Milky Way halo. As you, yeah, I'm sure heard, like that the Nobel Prize this year was awarded for, or at least half of it, for measurement of the mass of the supermassive black hole at the center of the Milky Way, and it's kind of that mass. So it's really like a massive object that we don't expect to be just kind of randomly orbiting around the halo. It should be at the center of a galaxy. So it's still a puzzle of what happened. And one idea I had was say, okay, well, let's try to predict where this object would be on the sky today, and try to follow it up. Because if it is some like undiscovered globular cluster or undiscovered dwarf galaxy, we should be able to see it if we just kind of know where to look on the sky. However, and if it's dark, then we might have some additional observations in that part that can distinguish between the dark matter subhalos that are low density and the black holes that are high density. However, if I took all of the kind of these models that live in this region of the space and produce that kind of gap and spur feature in the stream that we observed, and kind of plot them where they would be at the present, I get a map that looks like this. So here's a map of the whole sky, and turns out that with just that information, there are many possible orbits for the perturber to be on, and it can literally be anywhere on the sky today. However, it's not entirely hopeless, because if we color code these models by the relative velocity between the main part of the stream and the spur part of the stream, you can start seeing like different patterns. So there's like a blue chunk over here, which corresponds to negative velocities, and a red chunk over here that corresponds to positive velocities. And you can see that like the range here on the color bar is fairly small. It's just plus or minus 5 kilometers a second. So it turns out that there is a way to kind of narrow down this location on this, of the object on the sky, but we need to have very precise measurements of radial velocity. So here's kind of how the story develops next. I used the CFA telescopes in Arizona and MMT with a high resolution spectrograph to measure radial velocities of the stream stars at 4 locations in the mainstream. So this is shown in light orange, and the 4 locations in the spur, which is shown in dark orange. And when we sort of look into this relative radial velocity between those, you can see that there in these locations where we, at the same kind of location of the stream, have the measurements both in the main part of the stream and the spur, looks like there is not much of a difference. So even when we zoom in, it looks like there is less than a kilometer a second difference between these two objects. So that means that if we go back to our map, we can really rule out most of these color points and kind of just focus on the dark ones that are kind of plus or minus 1 kilometer a second. And when we do that, it turns out that this becomes a much cleaner looking diagram. So it's still a huge, and like this densest part is sort of covers 5,000 square degrees, but it is kind of a work in progress, and I think provides us with a very exciting possibility of actually locating the object that caused this feature in a stellar stream, and then ultimately learning whether it is dark matter or something else that happened to the stream. And so this is sort of where the story ends, or like where we are at with this GD1 stellar stream today. So it's not yet known whether it actually is dark matter or not. But I want to kind of leave you in the uplifting note that even if this object wasn't perturbed by dark matter, we now have so many stellar streams that we know of orbiting the Milky Way that for sure we can test this dark matter model in the future. So here I'll just play starting from one of the streams in the inner galaxy to the sample, or I'll cycle through 22 stellar streams that we have observed in the Milky Way, and for which we also have orbital information. So as they kind of are lighting up, you can see that they have been orbiting in different parts of the galaxies, and some are kind of really confined to the inner parts. And as we are zooming out, we are becoming more and more sensitive to anything that was happening in the outer parts of the galaxy. And as you saw before, this is kind of where we expect most of the dark matter to rely on to have most of the substructure. So it's exciting times for this sort of detective work within the galaxy, because we have now so many other leads to follow. So with that, I will thank you for your attention and answer any questions you might have.
If folks want to unmute themselves, you can ask away.
Dr. Bonaca,
Yes.
can you perhaps project how the Vera Rubin Observatory, when it comes online, might add to giving a clearer picture of location of dark matter?
Mm-hmm. Yes, that's a great question. And okay, I will go back to this slide. So I show you how here, like to select a clean picture of this one stellar stream, we used both the motions of the stars, so to kind of select stars that are moving all in the same way along the stream, and also the color information. And so what the Rubin Observatory will provide will just be colors of stars, or rather the motion constraints on motion will not be that precise. However, what will be really, really good is that it will go basically 5 magnitudes deeper than what we have over here. So we'll have just much or many more stars to select from, and thus kind of be able to better select stars that are part of the stream than of the kind of smooth Milky Way. And I did some calculations with kind of predicting how sensitive this is, and in this object that I showed was something like 1 million solar masses, that we are sensitive to here. With the Rubin Observatory, we'll be able to detect objects or signatures of objects that are even like a factor of 10 lower mass, so 500,000 solar masses. So this is going to be really a game changer, and especially, okay, and I'll flip back to this final figure where I'm showing the sample of stellar streams that we know of. So you can see that this is kind of a scale of 15 kiloparsecs, and we are like somewhere over here, basically, very close to the galactic center. And the stream that I talked the most is this long white one. And the reason is because it's so close to us. And what the Rubin Observatory will allow us is to kind of do this sort of analysis on basically all of these streams, or at least on the southern hemisphere where the observatory is, that are kind of all the way out in this outer parts of the galaxy. So yeah, it's going to be a very, very exciting time when the observatory starts collecting data, for sure.
Two things. One, are any of these streams, I mean, these seem to be pretty far outside of the galactic disk.
Mm-hmm.
Are any of these observable? If you do any kind of like, can you, I mean, we can see star clusters and things like that, you know, when we're observing at night, but are these streams, would we be able to see one? That's one question. And the other question is are any other people studying, say, the Andromeda Galaxy to kind of see this from the outside, where we're here, we're looking at it from the inside out, and Andromeda is so close and so large in the sky that we could potentially see this effect from the outside as well. And I didn't know if any of your colleagues or you were, I mean, the Milky Way is pretty big to begin with, but could you see it from the outside looking in? So those two questions.
Yes.
Oh, and thank you for a fascinating talk.
Oh, thank you. Yes. Okay. Let me answer the second one first, as we were talking about this. Yes, there are people studying the Andromeda Galaxy, and indeed, one of the big findings of a survey called Pandas, which is just a cute name, it has been that actually the stellar halo of the M31, the Andromeda Galaxy, has a lot, like one huge stellar stream, and that's the one that is a disrupted dwarf galaxy. It is. So all of these are like, most of these are kind of much lower mass, and you can see that they're kind of not really wrapping around. What we see around the M31 is, or Andromeda is a kind of stream that kind of wraps all around. So it is, yeah, much easier to observe it from the outside. However, we because it's such a huge object, it's slightly less sensitive to this small scale perturbations that we see in the or expect from dark matter or low mass dark matter clumps. So this is so I think people are now starting to think of using this approach of studying this low mass, like very thin stellar streams beyond the Milky Way, but they haven't been discovered yet because, again, they've been kind of hard to discover in the Milky Way, and just like haven't been seen outside the Milky Way yet. But I think now with there are some. We have good chances of detecting them with the Roman telescope, which is going to be a space-based mission that really kind of has the capability of in imaging of the Hubble Space Telescope, just with a larger, like much larger field of view. So which is required here because we really need like to image a huge part of the sky to detect those. And I think this sort of kind of segues a little bit into the answer to your first question, is whether you could see them. So I think, yeah, you could definitely detect these stars. So again, if I go here where I show this color magnitude diagram, so you can see there are some, anyway, stars that are kind of like this main sequence turn off, like this, yeah, just turns off is at 18th magnitude. And I think in one of the images that are shown in the observers report, you're detecting stars all the way to 20th magnitude. So it is possible to detect these stars even with the kind of equipment you are using. It's just that these are very rare stars. So if you kind of look at this, kind of what the scale is, you can see that this spans here 100 degrees, and you can literally count the numbers of stars. And so to maybe bring the point closer to kind of home, to give a perspective of how many stars you expect in the stream. So here's our one field with our spectroscope has kind of a square degree, and like in this densest part of the stream, we only had 10 stars. So yeah, it's so while you can detect them like individually, you wouldn't really be able to pick them apart unless you have this kind of wide map and with multiple colors, so that you can select those that are kind of most likely have the right colors to be part of the stream. Yeah.
Thank you. Thank you very much.
You're welcome.
Anna, so what you're looking for really are the perturbations in these star streams, right?
Mm-hmm.
Do you, in that last slide you showed, there were 22 of these star streams that, are those the only ones we know about, or are those?
There are a few more actually. These are just the ones that we have we have measured motions of them, so that I could calculate the orbits and kind of where they kind of how they have been moving. But in total there are something like 60 stellar streams that have been reported. And another reason why I only used like these stars where the motions have been detected is just that then it's a little bit we're more secure that these are actually real objects. As you can imagine, like the field has for a long time been operating in a way that we created maps that look like this, like the one I showed here. So here's just kind of a weighted density map where like each pixel like shows some probability of like this being of a star at a given distance at a given metallicity, and kind of looking at those kinds of maps and thinking and saying, oh, well, this looks like an overdensity. And so this is one of the most obvious ones, and turns out that it's real, but there have been then many detections that were, let's say, less convincing. And so it's, but it could be, anyway, I'm usually optimistic about those that it will turn out, but maybe just like the data hasn't been good enough to kind of detect their motions. But I think if they all pan out to be real, then in this kind of same volume, we will have more than 60 stellar streams. So it's really kind of a fairly dense web that they cover, and which makes me then very hopeful that we, like, if there are any subhalos, that we should like see some effects of them, because we just like have these patrollers that have been kind of going around like basically everywhere throughout the galaxy.
Interesting. And so these star streams that you show here, have they been examined closely enough to see the same sorts of? No, right?
Yeah,
that might give some insight if you know, maybe the star stream that you studied was just a fluke. You know, where do you know what I mean?
I do.
If you started to see more of the same with each of the star streams, then it would mean that they're.
Yeah, that's exactly right. That's exactly what we need to do. And I'm very excited about the next Gaia data release, which is happening on December 3rd. So really only a couple of weeks away. We'll have this proper motion measurements that are twice as precise, which means that we'll be able to kind of better separate the motions of stars that are kind of all moving in the same direction from the bulk of the stars kind of just rotating in the Milky Way disk or just randomly in the halo. I think we'll be able to secure those stars more precisely in these outer streams, which will kind of allow us to make the same sort of analysis we did for this nearby one.
Is there any other? This dark matter is so perplexing to me. You know, just is there, when
Not
you talk
just
about,
to you.
No. And I just like to look through my telescope. But does anyone, do we have any idea as to what, I mean, a clump of dark matter is all about? I mean, I know it's a relatively new sort of thing to think about and study, but do we have any indication of how you'd even get a clump of dark matter? I'm not even sure I know how to ask the question.
Yeah, it's
because you're looking for discrete structures.
Yeah, it's so the paradigm is that the universe early on was when kind of all of the kind of matter was mixed, and like after the Big Bang it was like a mostly like uniform universe, and there were just like very, very small like regions where there's like they were a little bit denser than the others, and because they were a little bit denser, then they started gravitationally pulling everything else like surrounding matter to it, and sort of growing into this kind of clumps of matter. And at the time, the dark matter and the normal matter were all kind of mixed, and were kind of behaving as the same thing. And it turns out that kind of those small clumps that of dark matter then were kind of then like small clumps that formed, that started merging together and forming these bigger clumps. And some of them, when they kind of merged together, they kind of meshed into this smooth part. But the kind of more recent arrivals, they retained like they remained as discrete clumps for a little while until they kind of have been there long enough, or maybe are on orbits that kind of plunge into the center and kind of get mixed in with the rest of the dark matter. But it's sort of the picture of kind of how these halos growing through like first forming those small clumps, and then those are growing as they're accreting together. And but for a while they do remain clumped as small clumps in this bigger halo. And what we expect is that kind of the gas, like the normal matter, follows those like inhabits those small clumps, but but only to some level, because like out of those very small ones, the gas can then just escape. But the dark matter still remains clumped because it has this sort of very high mass that kind of allows it to kind of become gravitationally bound and not just escape out of it.
Does the idea of dark matter and its ability to interact with normal matter, does that on these relatively small scales, does the idea extend out to the large scale structures of the universe? I mean, don't we see normal matter? It's like frothy almost, isn't it? Like just like galaxies on the surface of bubbles.
Yeah, it is. Yes, it's also because the gravity is as a long range force, so it actually does govern the whole structure, and it ends up being a lot like what you described. It's sort of, it has this filamentary structure where the galaxies are like in this kind of long filaments, and there are some people who actually study those, as you were saying, kind of the galaxies being on the edges of the soap bubbles, but there are then in the most of the universe, there are like these big voids, and people do study kind of statistics of voids in the distribution of galaxies to constrain some properties of dark matter as well, and also just kind of the typical distances between pairs of galaxies and other kind of such statistics on kind of very, very large scales to kind of understand, to test this dark matter model. And this is basically why this model of cold dark matter is so popular, because it predicts the observed distribution of galaxies on these large scales like perfectly. Like people have been searching for a long time now for kind of any deviations, and it always comes up just basically what is predicted by this model. So this is why it's been so popular, and why I and other people who kind of look at this small scale actually want to test it so much, because it kind of appears to be working perfectly everywhere else in the universe. It's just like that. It predicts that there's a bunch of these small subhalos that we haven't seen yet.
That's fascinating. It's wild.
It really is. Yeah, when you think about it.
Wow. Hey, are there any other questions?
I have another one if nobody else does. I don't want to hog it.
Go ahead, Mark.
All right. So you were talking about a black hole going through, potentially it's a black hole or a massive black hole.
Mm-hmm.
And that would disturb the stream extremely.
Yeah.
But dark matter, you say, does not have the same gravitational effect.
Mm-hmm.
I guess the question is about these dark matter blobs that are, have they not had a long enough time in the age of our galaxy to clump together enough to have an extreme effect? Or, I mean, it seems like the black hole seems to explain, or something similar size, what you're seeing in that one stream that you showed us.
Mm-hmm.
And that the dark matter blob wasn't enough to create that kind of a disturbance.
Yeah.
So
yeah, that's.
I know it's kind of like Rich's question. I'm not quite sure what the question is, but
No, yeah. I think well, anyway, I will give you an answer to what I thought was a question, and then you can come back to me if that wasn't what you were asking about. Yeah, you are perfectly right that it looks like what we need is not exactly what this model predicts, because yeah, that's another interesting feature of this dark matter model, is that it predicts what the kind of density profile of each individual clump of dark matter is. And it turns out that if you basically know the mass, you know its profile as well, that there's very little like deviation. If you can just kind of scale them up by mass, and you get the exact same density profile. And it's it's some profile. It's not like it doesn't have size 0 like the black hole. It has some finite size, which means that then at the center it has a lower density than the black hole would have. And what we are finding here is that we are actually, oh yeah, I guess I can go to that slide, that we are actually preferring something that would have a higher density, or in this figure it would have a smaller size. And so that's then slightly kind of disfavors this interpretation that this is at least this kind of regular looking model of dark matter. However, those 3 models of dark matter that I showed are really just kind of the basic classification. Kind of in each of them, there's just like further kind of subdivisions you could have. And one alternative that has been also popular is a model in which dark matter kind of interacts with itself. And then in certain models of those, they are predicting that because of those self interactions, that they could form like a slightly denser center of those subhalos, so that they actually might live somewhere here. but this is all very much kind of theoretical work. So that's why we're kind of trying to go at this from the kind of observational stance and predict, like if we could find this object on the sky, then we might think of ways to actually measure what the size is and what the mass is in different ways, and use that to kind of rule out certain models of dark matter. But yeah, I think you're right that it does depend on this kind of the central density of the object, and that what we are finding is something that looks more like black hole rather than this kind of usual expected dark matter subhalo. And this might actually be telling us that this is maybe not the right model, that maybe if it turns out that it is dark matter, then we would probably need like a different kind of dark matter.
Yeah, that's what I was going to say. Yes, I think it kind of leads me in the direction of the fact that maybe there's more than one type of this mysterious dark matter, or how, you're right, how it interacts with itself. We don't know what it is, and so, all right. Yes, you got the basic answer to my question, which is we still don't know a lot, but I actually think the observable idea is, rule that out first before you,
Yes.
have to redefine dark matter, which
Yes.
is not even defined yet.
Yes, that's true. And I talked to one researcher who studies these self-interacting dark matter models. When I heard that they are predicting those kind of denser clumps, and I kind of showed him this figure, and it's like, oh, I think this really might be an issue because like this kind of track of dark matter subhalos is offset, and he was like, come on, this is kind of again that astronomers thing, order of magnitude. He was like, yeah, that's basically the same. Yeah. So he wasn't very worried about this. So I think this also might be another case of if we find more evidence that it's not just like this one stream, but if for every single one we need something that is much denser, then it might be kind of time to start thinking about those alternatives. But for now, I guess it's just kind of interesting, but not quite like a crisis mode yet for the kind of regular model of dark matter.
Dr. Bonaca?
Yes.
Thanks for a very interesting presentation. Just to expand on what the last, what Rick and others have mentioned, dark matter is thought to be non-baryonic matter, and projecting forward, stay locating positional where dark matter is by getting better data. Do you think the mathematical algorithms currently in use can actually help narrow in on the nature of dark matter, since it is non-baryonic matter?
Yeah, that's a great question. And yeah, sorry, I know you emailed this, and I was saying, kind of halfway through the talk, remember that I wanted to mention it when I was discussing these models here, and then but I forgot. But yeah, that's a great question of kind of how reliable are these kind of physical and mathematical models of dark matter. And kind of because all we have here are basically computations that we did on on computers, so numerically, and so it turns out that at least for these kind of non-interactive models, like just the cold dark matter and this warm dark matter, which is very similar, just has like a different mass, but the dark matter is not interacting either with itself or with the baryons, that those are very simple. So because you just kind of have to solve gravity, and then it's kind of a little bit of a question of how you ensure that you can simulate that the system at the right resolution. And so there's, I think, some work to be done now that we are finding evidence of stuff happening in the Milky Way. We would like to understand like the populations of those very small clumps, but also like throughout the whole Milky Way. So we need sort of a large simulation box, but then also like have a very tiny size. So we kind of need a lot of dynamical range to resolve. So there's, I think, a little bit of a kind of numerical issues of how we do that. But it's pretty much, I think that's sort of more of a kind of coding or engineering issue. I think the physics is kind of mathematics behind the model is well defined and understood how to deal with that. Some of these different models, and in particular in this kind of fuzzy dark matter model where there's like this is a sort of a quantum field, those are, well, first of all, much more recent. And they have only recently become sort of considered by the community more. So the state of simulations in this case is not as advanced as in this this kind of standard dark matter paradigm. So I think here there's a lot of improvement that can be made. And I think specifically in this case, this I think this is a simulation of a dwarf galaxy and not even the Milky Way size galaxy. And this is because it's very expensive to calculate this, solve these equations, because in addition to kind of solving the gravitational forces, you also need to solve the kind of the Schrodinger's equation, because these are the quantum fields that you're solving. And so that becomes very expensive. So I think that's still true that no Milky Way like galaxy has been simulated in this cosmology like all the way to the present. I think they started simulating them, but kind of stopped in the early universe because like you just like didn't have the time yet to continue simulating them all the way to the present day. So yeah, there's a lot of, I think, numerical work left to be done here. And sort of to tie to the previous question, yeah, it might be that, what we are finding is some evidence of non-standard dark matter. And so I think it is definitely worth exploring these alternatives.
Oh, thank you.
Thank you.
Just to put the particle mass here on this slide into perspective, a particle mass of approximately 10 to the minus 22 electron volts. How does that equate to things we know about, like a quark, for example, or a proton?
Okay. So
I don't know how to convert electron volts in my head to.
Yeah, I think proton, like I think that's like 100 GeV. So it's like favor. Yeah. Electron is, I think, 0.5 mega electron volts. So I guess 500 kV. Yeah.
Yes.
So.
Or anyway, if someone, like, if I said something wrong, please correct me.
It just boggles my mind that,
Yeah, this is like very, very light, like way. So yeah, definitely like the particles we know of are on this like left-hand side.
Sure.
Yeah. And yeah, I don't know about quarks. Sorry, I guess you did ask about quarks. I don't know, yeah, where they would be.
They're like 10 to the, I can't remember.
I don't think they're
10 to the minus 15th. I can't remember.
Yeah.
So that last slide is really just showing quantum fluctuations, right?
Yeah. Those are, and it has this kind of soliton core that kind of is collapse at the center. That is kind of
that's pretty crazy.
This model that like is fairly constant, but maybe at the changes a little bit on the outskirts, and all of these are basically quantum fluctuations. And this, I mean, partly this is why this model has been put forward, because so the issue was that, we see the Milky Way and we see the satellite galaxies, and we don't see these small clumps. And in this model, this mass is chosen such that you don't form them at all. like you just formed those halos that have galaxies in them. So so that's kind of how this mess is chosen. If you would decrease this mass further, then that would be a problem, because then it wouldn't predict the even some of the dwarf galaxies to have dark matter. But since we know we do, then it's kind of this kind of mass scale works out to just kind of say like, okay, we only form dark matter halos down to the kind of dwarf galaxy size and nothing beyond. But then it does predict that this is this constantly fluctuating medium.
Wow, that's pretty cool.
Yeah, no, it's wild. And actually, yeah, I think there are some people at MIT, like Mark Vogelsberger's group, even though that are running such simulations in collaboration with a few other people. But yeah, there's some local expertise. Yeah, I don't know if you kind of have series, kind of topical series or so, but yeah, they probably would have like cool simulations showing how like these change in time. Yeah.
Wow.
Yeah.
Are there any other questions?
Yeah, how do you know there's only one perturber? I mean, isn't in reality, there's probably lots of things perturbing it. So how do you kind of handle that?
Yeah, that's a great question. And yeah, we like here only focused on this like one gap and or rather, yeah, let me show it here. I was just trying to reproduce this picture over here, and I was assuming that this just happened in like one go. In principle, like you might imagine if this is maybe in some sort of resonant orbit that always kind of passes through the same like crosses that object on every passage, and this might be something cumulative. We haven't like explored it yet. On the other hand, there's like this small amount of fluff over here and another gap over here, which we in this model that I created, I just said that this is where kind of the globular cluster died, basically. So this is kind of where why there's nothing left, and the two kind of ends are kind of drifting apart. But it could be that this is another like impact, and this is another kind of blob that has been pulled out. So yeah, those are great questions, and this is very new work, and the field kind of has proposed this test of using stellar streams as detectors for dark matter like 20 years ago, but really we only have had this data in the past couple of years. And it came with these surprises that of like stars outside of the stream, yeah, there's just a lot more to be done to get a more comprehensive view of what's happening. But yeah, that's a great point. And actually, okay, let me just add one more thing that like in this figure where I showed kind of where we expect the object to be, you can see that this is not like a random distribution. It looks like it's a kind of a great circle or kind of on the sky. And it turns out it actually corresponds really well with the orbit of the Sagittarius dwarf galaxy, which is kind of this massive galaxy that is also disrupting in the Milky Way. So if really this, whatever the perturber is associated with this dwarf galaxy, you could imagine this kind of actually this repeating scenario, or like maybe seeing something else from this debris field of the dwarf galaxy, even if it's not exactly the same object, but something similar, like always happening at a similar position in the stream, that it actually might not be just a single thing, but like multiple events that happened. Yeah, but that's all like TBD.
Excellent. Well, Anna, thank you so much for a fascinating talk. Thank you for sharing your work with us.
Well, thank you for having me and for being so enthusiastic and having so many good
If
questions.
everybody unmutes, we can give you a nice round of applause. It's a little hard on Zoom, but
Thank you.
We can clap.
we can all clap. Let me just share my screen one more time. Don't go away just yet, Anna. People will stick around for a little while, but I just wanted to officially sort of close the meeting by telling you all that the next monthly meeting will be on December 8th at 8 p.m. And our next quarterly board meeting will be held on Thursday, January 7th at 8 p.m.